Welcome to the new topic of total surface area, also known as TSA, and volume. And this will be looking at the work within chapter 6 of the measurement topic from the textbook. This is lesson 1, area consolidating. And the learning goals for this one is to look into area conversion and area formulas for different closed shapes or sector circles or composite shapes. And the success criteria is to be able to find areas of parallelograms, trapeziums, rhombuses and kites, and also calculate the areas of composite shapes. I've taken a few examples from exercise 6C, and we're going to be looking into a few things. The first thing is looking into the conversions of units of area. So what we're so used to is converting millimeters to centimeters to meters to kilometers, but now we're doing it in the form of volume. So what this question is saying here is we're going to convert these areas to the units shown in the brackets. So this is 2.5 squared centimeters, and we're going to convert this to squared millimeters. Now we've got this little conversion of units of area chart at the side, and we're going to start at centimeters squared, which is this one here, and we want to go to millimeters squared. And what we have to do is multiply by 10 to the power of 2. So let's get 2.5 as squared centimeters, and we're going to multiply this by 10 to the power of 2. Now 10 to the power of 2 just means 10 times itself 2 times. So this is just 2.5 squared centimeters multiplied by 10 times 10, which is just 100. And so when you put this into the calculator, which I'll grab along here, 2.5 multiplied by 100, let's try that again, 2.5, not 2.0, multiplied by 100, here we go, is 250. So the answer here is 250 squared millimeters. Now to put some context to this, let's say for instance that I had a very, very tiny box of some sort. It's really small. And it's a box of this shape. Now we don't know what shape this is. It could be rectangular, square. But what we do know is that approximately 2.5 of these small little blocks, you know those little wooden blocks you used to get in primary school? We know that about 2.5 of these, so there's 1, there's 2, and just a small little sliver of half. My drawings are not accurate. All right, so this is 2.5 or 2.5. These can fit into this box here. All right, so this is 2.5 squared centimeters. And we're saying, well, how many squared millimeters can we get? So how many small little ones? Small, tiny little so cute, squeeze them. How many of these can fit within this box? And this is saying, well, we can fit 250 of these, considering that we can fit 2.5 in this box initially. That's what this conversion means. We're going to do this again for B, but this time we're going to convert squared centimeters to squared kilometers. So if we want to go from squared centimeters to kilometers, we have to bypass the squared meters to get to squared kilometers. So we have to divide by 100 squared and then divide by 1,000 squared. And remember, 100 squared means 100 times 100, and 1,000 squared means 1,000 times 1,000. So I'm expecting to get quite a small answer for this. So let's first do, this is 2 million. 2 million, I'll put these little comments here. 2 million, and we're going to divide this by 100 squared, and then again divide this by 1,000 squared. And we can just put this straight into the calculator. So let's put 2 mil, 1 0 0 0 0, there we go. Let's divide this by 100. And I can just press that square button here. And sometimes when I press the 0 once, it comes up with 2 zeros. It's a bit of a weird glitch. Quite annoying sometimes, but there we go. And divided by 1,000 squared. Now, if you get this answer 1 over 5,000, you just press the SD button, and you'll get 2 times 10 to the power of -4. Now remember, this is scientific notation, so this is that little negative to the negative 4 or power to the negative 4 that just indicates that there are 1, 2, 3, 4. So it's negative 0.00002, and this is squared kilometers. So obviously not that much square kilometers can fit into something that's 2 million square centimeters. Now I just realized I've overcompensated for this. I've added one too many zeros. Thought it looked a bit. There we go. Count how many zeros there are, but what that power is, and just put the decimal point there. Next thing we're going to do is be looking into the areas of these three basic shapes. Now I'm not going to go into the construction of how these formulas work. I'm just going to use the formula based on whatever shape they give me. So in this case, we've got the first one, which is a trapezium. A trapezium has 3 points of references: the base, the top length here, and the height from where the two lines that are parallel, it's perpendicular to that. So these two lines here are parallel, the 2 centimeters perpendicular, and this will be the perpendicular height. And when you get these different sets of information, you just plug it into this area, which is just half multiplied, there's a hidden multiplied, a plus b added together, multiplied by h. So this is half times, so a plus b is just the top plus the bottom, so 3 plus 5. So 3 there and the 5 there, and then multiply this by whatever the perpendicular height is, which is 2. So half times 3 plus 5 is 8 times 2. 8 times 2 is 16, and half times 16, or half of 16, is 8. So our final answer in this case is just 8 squared centimeters. And all this means is if I were to get a squared centimeter, 1 by 1 centimeter square, exactly 8 of these can fit in here. Now obviously it will look a bit weird, but you can cut it and manipulate it so exactly 8 can fit into here. For question B, we're looking at a triangle. Any triangle, you just need to grab the base and the height and multiply them together and just half that result. Because a triangle is always half of the size of either a parallelogram, a rhombus, a rectangle, or a square. So we're just getting base times height and just dividing it by 2 or halving it. So in this case here, our area, half times base times height, which is just half times our base is 5.8 and our height is 3.3. So when we plug this into the calculator, so 5.8 times 3.3, and then we just divide that by 2, press SD, 9.57. So this is 9.57, I'll put that in a different color, 9.57 squared meters. For C, we're getting the area of a circle. And the rule for the area of the circle is pi times radius squared, where r is the radius, or pi times r squared, where r is the radius. So to give a bit of insight, this is a circle. From the center to the edge, we have a radius. From a straight line, from exactly edge to edge, we have what's called the diameter. And the radius is always half the size of the diameter. If a diameter has been given to you, we know this is 1.06. We can't necessarily use this length in the formula because it's giving us a full length. We need to get the radius, so we need to get half of this. So our R value in this case is just whatever 1.06, whatever half of that amount is, which is 0.53. So our radius in this case is 0.53. And then we'll use this amount here, 0.53 kilometers, for our area formula. So to get the area, it's pi. Now remember, pi is just a ratio of the diameter with the circumference, which you should have learned this within year 8 and year 9. We just use the calculator here to get pi. You don't use 3.14. You want to be as accurate as you can. So you want to press the shift button and press this times 10 to the power x button here. And you can see right there, there's a little pi symbol that is indicated of the pi. So let's get pi, multiply by 0.53 squared. Again, just use that button for the squared, equals, And the answer for this one is 0.882. Now, let's just see how many decimal places. 2 decimal places where necessary. So it's just going to be 0.88. 0.88 square kilometers. So the amount of squares we can put within here seems a bit really counterintuitive, but we're just shy of a kilometer, even if our radius is 1.06. Because you've got to remember that there's this little area along here, here, that we've got to compensate for, which is not necessarily being filled in. So it's very, very close to a kilometer, a square kilometer, but we're just not there yet. All right, we've got 2 more examples, and right here we're going to be looking at the area of a sector, and we're going to look at the area of a composite shape. A sector just means a circle that has been cut into a certain shape. I like to think of this as the Pac-Man shape. If we have a little eye there, it kind of looks at Pac-Man and goes wonka, 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 wonka. Now, obviously, we can't necessarily get the area of the full circle. We can work it out, but you'll notice that there's like a pizza chunk that's missing. So we're expecting to get an answer that's just a little bit less of what a full circle is, because we're only getting a proportion of that. And so to get the area of this, we need to just use the normal formula of pi r squared, but then multiply it. We have to multiply it by what's called theta, and get theta, which is the internal angle within the circle, and divide it by 360. Because when you do this, you're getting what's called a proportion of that area by multiplying by what's called the multiplicative factor. We're getting a proportion of this, and it's 360 because it's 360 degrees within a full circle. So the first thing we need to do is, well, if we know there's 360 degrees within the full circle, and we know this external degrees is 80, to work out that first internal part, we just need to find the difference, 360 take away 80. And this will give us the internal degrees of 280. So the first thing we know that within here is 280 degrees. The second thing we're going to do to get the area of this is just literally plug this amount as a fraction into here. So times it by pi, times by what a radius is. A radius has been given as 3 centimeters, and we're just squaring it, or 3 times 3. Now look at this. Let's just assume that we've got a full circle. Okay, let's assume we've got a full circle, and we'll just put the formula in as normal. Pi, so shift and that, times 3 squared, SD, 28.27 squared centimeters. So very close to 30, okay? So about 28.27 of these little squares can fit in here. That's assuming it's a full circle. We now just want to actually multiply this by 280 over 360. So let's actually put this in straight as a new line. Get our fraction button, 280. So remember, we're expecting an answer this a little bit lower. Multiply this by shift pi times 3 squared. So it's 7 pi, or 21.99. So area is 21.99 squared centimeters. Because when you multiply this by a fraction that is lower than 1, and this fraction is lower than 1, any fraction where the numerator is smaller than the denominator, 79, so 0.77. This is 0.77. When you multiply the 0.77 by a full quantity, we're going to expect an answer that is smaller than the quantity itself, because we're getting a proportion of that. And to get that proportion, that's where we use that 360, okay? So that gives you a bit of intuitive feel of where this formula comes from, because we're dealing with just a sector or an area, a chunk of that full circle. And with that insight, we're gonna have that help us determine the answer to what the area of this composite shape is. Now, composite shapes, that's A and this is B. Composite shape is the trickiest one out of all of them, because you have to, it's not obvious what you need to do. You kind of have to use a bit of problem solving in order to figure this out. So what we do know is that let's just assume that this is a full rectangle. We have 5 meters on the bottom and we have a 5 and 5 there. I know that this is 5 here, indicated by that 2 dashed lines. This is just saying that anywhere I see 2 dashed lines is also 5. And because I can see 2 lots of them, this length here has to be 10 meters. It's 2 lots of 5. Now let's just assume that we're just trying to get the area of this full thing. And that's just length times width, which is 10 times 5. So let's just call this area 1. So we know that area 1 is just equal to 10 times 5, which is 50 square meters. But the thing is, we know that we're not looking for the full area, we're looking for a portion of that full area. So there's this quarter circle that's kind of cut into it, and it's been a chunk of that has been taken off. And we don't necessarily know what the area of a quarter circle is. We know what the area of a full circle is. So let's just work with that and then maybe just find a quarter of what that area is. So to get this area 2, which I'm gonna say, let's call this part area 2. Area 2 is just whatever this area is, this square, taking away a quarter of a circle. And once we get that little area in there, we can either take that away from 50 or add it to whatever this area is. There's different ways to approach this. All right, so let's work out this area here, this chunk. We'll call this one area 2. So area 2, this is going to be only a quarter of what pi r squared is. Only a quarter, not a half, a quarter, there we go. And what's our radius? Our radius is just that length from here to here, which we kind of already know. It's 5 meters, because it's 5 meters all around here and here and here. So we've got our radius. Our radius in this case is 5 meters. So let's just plug in what we do know. So a quarter times pi times 5 squared. Put this into our calculator. So a quarter, 1/4, multiplied by shift pi, multiplied by 5 squared, SD, 19.63. So this is approximately 19.63. So to get that full area, let's just take 50, which is the whole area, assuming it's a rectangle, and just take away that quarter circle of 19.63. So the composite shape area, so composite shape, this is area 1, take away area 2. Or in other words, this is 50 square meters. I should put square meters there. Take away 19.63 square meters. 50, take away 19.63, and we get 30.37. 30.37 square meters. So composite shapes is requiring you to work out different types of shapes and either adding or subtracting to each other. There were different ways to approach this. You've got to use your problem solving skills and your logical skills in order to figure these ones out. Not all of them are simple. All of them do have different ways to approach them. As long as you're getting the answer correct, that's all that matters. We'll wrap it up here, keep it under 20 minutes. Go ahead and check the log sheet to see what questions you want to do. Now, I will be showing you this within the team meeting, but the way that the log sheet works for this year for remote teaching is that you can either do the textbook exercises, Khan Academy, which is something again that Mr. Sturgis's class is doing. I can set that up if you wish to, but we've also implemented a new thing called spreadsheets, which is you can use Microsoft Excel to look at the different areas of shapes. Now, it's called 12 areas of shapes which can be found within Compass. I'll be talking about this within our Microsoft Teams meeting anyways. If you want to just keep to the traditional textbook exercises because that's the easiest approach for you, then you're looking into exercise 6C, left-hand side for questions 1, 2, 3, 5, and 7. See how you go, and I'll see you guys in the next video. Bye-bye.